Your roof is exposed to one of the largest heat sinks imaginable every night, yet almost all of that cooling potential goes unused. I'm not talking about wind power, solar panels, or another expensive machine. I'm talking about the open sky. With a properly coated aluminum panel, it is possible to release heat from a building directly into the upper atmosphere and eventually into space. The panel requires no compressor, refrigerant, or motor. Under favorable conditions, each square meter can provide roughly 30 to 40 watts of passive cooling. The basic materials can cost as little as $20 to $30 per square meter. This process is known as radiative sky cooling. In this video, I'll explain the physics behind it, where it works best, what its limitations are, and how a practical home-built system could be assembled. To understand why this matters, consider what conventional cooling demands from an off-grid electrical system. A small window air conditioner may consume anywhere from 500 to 1,500 watts while operating. An efficient mini-split can still draw several hundred watts for hours at a time. During a long summer day, cooling alone may consume multiple kilowatt hours of electricity. That creates a chain reaction. You need enough solar capacity to generate the power. You need batteries large enough to store it. Then you need an inverter, wiring, charge controllers, mounting equipment, and backup capacity for cloudy days. The air conditioner may be only one part of the total cost. A sufficiently large lithium iron phosphate battery system can cost several $1,000s before the rest of the equipment is included. Even after making that investment, every hour of air conditioning continues pulling stored energy from the system. Radiative cooling approaches the problem from the opposite direction. Instead of generating more electricity to operate a machine that removes heat, it allows a surface to release heat without using electricity in the first place. The principle begins with thermal radiation. Every object warmer than absolute zero releases electromagnetic energy. Your body radiates it. The ground radiates it. Buildings, vehicles, trees, and even cold objects radiate some amount of energy. Most objects at ordinary temperatures release much of that energy as infrared radiation, which human eyes cannot see. Normally, Earth's atmosphere absorbs a large portion of the infrared energy leaving the surface. Atmospheric gases then emit some of that energy back toward the ground. But the atmosphere does not absorb every infrared wavelength equally. There is a region known as the atmospheric transparency window, located roughly between wavelengths of 8 and 13 micrometers. Within this range, infrared radiation can pass through the atmosphere much more easily than at many surrounding wavelengths. A surface designed to emit strongly within this window can release heat upward with relatively little of that energy being returned. In clear, dry conditions, some of the radiation effectively escapes through the atmosphere toward the cold background of space. That is the foundation of radiative sky cooling. People were using versions of this effect long before anyone understood infrared physics. Historical accounts describe shallow containers of water being left beneath clear skies in parts of India and Iran. Under the right nighttime conditions, the water could form ice even when the surrounding air remained above freezing. The water was losing heat through radiation faster than it was gaining heat from the air around it. Modern radiative panels use the same natural process, but they are engineered to make it more useful and predictable. However, you cannot simply place an untreated sheet of aluminum on a roof and expect exceptional results. Bare aluminum reflects infrared radiation very effectively. That makes it useful in reflective insulation, but it also means it is not naturally an ideal thermal emitter. To turn the aluminum into an effective radiator, its exposed surface must be covered with a material that has high infrared emissivity. A simple white coating can serve two purposes. First, it helps reflect incoming sunlight so the panel absorbs less solar energy. Second, depending on the composition of the coating, it can release thermal radiation much more effectively than bare metal. Nighttime cooling is comparatively straightforward because there is no direct sunlight heating the panel. Daytime cooling is much harder. At midday, sunlight can deliver close to 1,000 watts of energy to every square meter of exposed surface. Because the radiative cooling effect may only remove a few dozen watts per square meter, even a small amount of absorbed sunlight can overwhelm it. Researchers therefore develop surfaces that reflect nearly all incoming sunlight while still releasing infrared energy through the atmospheric window. In 2014, researchers demonstrated a specially engineered multi-layer material capable of remaining below the surrounding air temperature in direct sunlight. The structure reflected approximately 97% of incoming solar energy while emitting strongly in the desired infrared range. During testing, the surface reportedly reached nearly 5 degrees Celsius below ambient temperature around solar noon. The important discovery was not that every homeowner should reproduce that exact multi-layer structure. It was the demonstration that passive radiative cooling could continue functioning during daylight when the material was properly designed. That result encouraged other researchers to search for materials that could be produced more cheaply. One later design used a polymer film containing microscopic glass particles. The particles helped the material release infrared radiation, while the film reflected much of the sunlight striking it. Because the material could potentially be produced in rolls, it offered a path toward much lower manufacturing costs. Commercial systems have also used radiative panels to assist conventional air conditioning and refrigeration equipment. Instead of attempting to cool an entire building directly, the panels cool circulating fluid before it reaches the mechanical refrigeration system. By lowering the fluid temperature in advance, the compressor has less work to perform. Testing on commercial buildings has reported electricity savings in the range of approximately 12% to 20% under favorable conditions. That hybrid approach may be one of the most practical uses of the technology. Radiative panels do not necessarily need to replace a complete cooling system. They can reduce the temperature of water, refrigerant, a roof surface, or incoming ventilation air before conventional equipment takes over. For a do-it-yourself build, the simplest design begins with a flat metal emitter. A sheet of aluminum between approximately 0.02 and 0.04 impressions thick is sufficient for experimentation. Common alloys such as 1100 or 3003 can work because the metal mainly serves as a lightweight, thermally conductive base. The exposed surface must then be coated. One documented low-cost approach uses white exterior acrylic paint containing titanium dioxide. Titanium dioxide is already widely used as a white pigment because it scatters visible light effectively. Some experimental recipes increase the titanium dioxide concentration by adding additional powder to the paint. A mixture containing approximately 10% to 15% titanium dioxide by weight is often suggested for small-scale testing. The coating should be applied in several thin, even layers, rather than one heavy layer. Uneven paint can create areas with different thermal behavior, while excessively thick coatings may slow heat transfer between the metal and the surface. Once the emitter is prepared, it needs to be isolated from unwanted heat. Placing the aluminum directly against a hot roof would allow heat from the roof to flow into the panel. The panel might still radiate upward, but much of its cooling capacity would be spent removing heat from the roofing material instead of cooling the intended water or air loop. A layer of foil-faced polyisocyanurate insulation can reduce that heat transfer. 1 or 2 inches of rigid foam beneath the panel should be enough for an early prototype. The aluminum faces the sky, while the insulated side faces the roof or mounting frame. The panel should also have as much exposure to the open sky as possible. Nearby walls, trees, roofs, and other structures emit infrared energy toward the panel. If half of the panel's view is blocked by a warm building, its performance will decline. An unobstructed upward view is ideal. Tilting the panel may help shed rain and improve its view of the sky, but the best angle depends on the mounting location and surrounding obstructions. Unlike a solar panel, it does not need to point directly toward the sun. In fact, reducing direct solar exposure may improve the performance of a basic homemade coating during the day. The simplest panel cools only itself. To move that cooling effect indoors, you need a method of transferring heat to the panel. One option is a water loop. Soft copper tubing can be bonded to the back of the aluminum in a serpentine pattern. Water flows through the tubing, transfers its heat into the aluminum, and returns slightly cooler. A small 12-volt circulation pump can move the water between the rooftop panel and an indoor heat exchanger. For an inexpensive prototype, an automotive heater core can serve as the heat exchanger. A fan blows room air through the heater core while the cooler water circulates through it. This resembles a very basic fan coil system, except the water is being cooled by the sky rather than by a compressor. The tubing must have good thermal contact with the aluminum. Soldering may work in certain configurations, although bonding copper directly to thin aluminum can be difficult because the metals behave differently during heating. Thermally conductive adhesive, mechanical clamping, or a compatible heat transfer compound may be easier for a small prototype. Builders should also plan for condensation. If the circulating water or panel surface drops below the dew point, moisture may collect on the tubing, panel, or indoor heat exchanger. Condensation lines and corrosion-resistant materials may therefore be necessary. A transparent cover can improve performance by reducing convection. Even when the panel is radiating heat upward, warm air moving across its surface can transfer heat back into it. Wind may increase that convective heat gain. A thin polyethylene film stretched above the emitter with a small air gap can reduce direct contact between the panel and the surrounding air. Certain polyethylene films allow a useful portion of long-wave infrared radiation to pass through while limiting convection. This permits the panel to continue radiating upward while receiving less heat from warm, moving air. The cover must not rest directly on the painted surface. A gap of roughly 1 or 2 inches allows the panel to radiate without the film conducting significant heat into it. Material choice matters. Galvanized steering may appear to be an inexpensive alternative, but its zinc coating can weather differently and may interact poorly with certain titanium dioxide coatings under prolonged ultraviolet exposure. Aluminum is lightweight, easy to obtain, and resistant to ordinary corrosion. Stainless steel may last longer in harsh environments, although it is heavier and usually more expensive. The finish system requires very little electrical power. The panel itself uses none, but a water pump and indoor fan will consume a small amount. Those components could be powered by a compact solar panel and a small battery, rather than a full-size off-grid cooling system. Still, this technology has important limitations. The biggest is atmospheric humidity. Water vapor absorbs infrared radiation. In a dry desert climate, the atmospheric window is relatively open, allowing more heat to escape. In a humid climate, additional water vapor absorbs and re-emits more of that radiation. The sky appears warmer to the panel, reducing the amount of net heat it can reject. A panel that performs well in Arizona may produce much weaker results in coastal Florida or Louisiana. Nighttime performance may fall from several degrees below ambient in a dry climate to only 1 or 2 degrees below ambient during humid conditions. Clouds create another problem. A clear sky provides the best view into the colder upper atmosphere. Thick clouds emit infrared radiation back toward the ground, acting almost like a warm ceiling above the panel. Thin, high clouds may reduce performance moderately. Dense, low cloud cover can nearly eliminate the cooling advantage. Radiative sky cooling therefore works best in places with dry air, frequent clear skies, and limited obstruction above the panel. The technology also provides cooling power, not electrical power. It cannot charge a battery, operate appliances, or replace a generator. A panel producing 40 watts of cooling is removing heat at a rate of 40 thermal watts. It is not producing 40 watts of usable electricity. That distinction is important. A single square meter will not cool an entire home. The cooling output of a small panel may be useful for reducing the temperature of a water tank, cooling a small insulated enclosure, improving sleeping comfort, or assisting another system. Cooling a complete house would require a much larger surface area. A 1,200 square foot home might need somewhere around 20 to 40 square meters of effective panel area, depending on insulation, air leakage, weather, internal heat sources, and the desired indoor temperature. That equals approximately 215 to 430 square feet. Even then, the system would provide only tens of watts per square meter, while a conventional residential air conditioner may deliver several thousand watts of cooling. This is why radiative cooling should not be marketed as a direct $22 replacement for every air conditioning system. Its strongest value may come from reducing baseline heat gain, pre-cooling water, assisting nighttime cooling, lowering roof temperatures, or decreasing the workload placed on a compressor. A homeowner could begin with one small test panel instead of covering the entire roof. Mount temperature sensors on the panel, in the circulating water, and in the surrounding air. Record the results over several clear and cloudy nights. That experiment will reveal how well the concept performs in the local climate before more money is invested. A basic prototype could include a flat aluminum panel, a high emissivity white coating, rigid insulation beneath the aluminum, a simple mounting frame, a clear polyethylene convection cover, copper or plastic tubing for water circulation, a small 12-volt pump, a compact indoor fan coil, temperature sensors for measuring performance. The first goal should not be cooling the entire building. The goal should be proving that the panel can consistently lower the temperature of the circulating fluid. Once that is established, additional panels can be connected in parallel or in a carefully designed series. Parallel plumbing may help each panel receive relatively warm water, improving heat transfer, while series plumbing may produce colder outlet water but reduce the cooling rate of later panels. Pump speed will also affect performance. If the water moves too quickly, its temperature may drop only slightly on each pass. If it moves too slowly, the panel may become colder, but the total amount of heat transferred per hour could decline. The ideal flow rate must be determined through testing. The economics depend heavily on the application. A small homemade panel may cost only a few $dozen, but a complete system also requires plumbing, pumps, insulation, mounting hardware, sensors, an indoor exchanger, and possibly weatherproofing. A full roof array would cost considerably more than the price of one aluminum sheet. However, the system has no compressor, no refrigerant, and few mechanical components. The primary moving parts are the circulation pump and fan, both of which are inexpensive compared with a conventional air conditioning compressor. That could make maintenance relatively simple. Radiative cooling may never become a universal replacement for air conditioning. In humid, cloudy locations, it may provide only modest benefits. In a dry climate with clear skies, however, it can become a useful part of a larger cooling strategy. Pair it with strong insulation, exterior shading, reflective roofing, nighttime ventilation, thermal mass, and an efficient mini-split, and the combined reduction in electricity use could be meaningful. The most interesting lesson is not that one painted panel will magically cool an entire home. It is that the sky can function as a passive heat sink, and almost every conventional building ignores it. We normally think of a roof as a surface that absorbs sunlight and transfers heat indoors. With the correct materials and design, part of that same roof could release heat upward instead. That creates several possible uses. A panel could cool water overnight and store it in an insulated tank for use the following afternoon. It could pre-cool the liquid entering a mechanical chiller. It could reduce the temperature of a battery enclosure, greenhouse, workshop, food storage room, or sleeping area. It could also be integrated into roofing materials so the building rejects more heat before the air conditioner ever turns on. Researchers and manufacturers are still working on coatings that are inexpensive, durable, weather-resistant, and effective in both sunlight and thermal infrared wavelengths. As these materials improve, radiative cooling may become less of a science experiment and more of a standard building feature. For now, it is best treated as a promising passive technology that can supplement conventional cooling rather than instantly replace it. But in the right environment, even a modest reduction matters. Every watt of heat removed passively is one less watt the air conditioner must remove mechanically. Every degree the water is pre-cooled reduces the load placed on the compressor. Every hour of nighttime cooling preserves more energy in an off-grid battery bank. That is where the real opportunity lies, not in producing more electricity, but in needing less of it. So consider your own property. Do you have clear nighttime skies? Is your climate relatively dry? Do you have an unobstructed section of roof or yard? Could you use cooled water at night or store it for the following day? If the answer to those questions is yes, a small radiative cooling experiment may be worth building. Start with one panel. Measure everything. Compare clear nights against cloudy nights. Track humidity, ambient temperature, panel temperature, inlet water temperature, and outlet water temperature. Let the results from your own location determine whether the system deserves to be expanded. Would you rather experiment with a passive cooling array for a few $100s, or put that money toward a larger mini-split and the solar equipment needed to run it? Leave your answer below. And in the next video, we'll examine another method of moving heat without relying on an expensive battery bank. An underground thermal storage system designed to hold energy for months instead of hours.